Hello guys, we want to solve some common question under thermodynamics. Said what? What is the total energy of 1 mole of a diatomic gas at the same temperature if 1 mole of a monoatomic gas has a total internal energy of 3.7? So E is equal to, for diatomic gas, is what? 5/2 nRT for a diatomic gas. This is for diatomic. Then for monoatomic gas, we have what? M mono is equal to what? 3/2 nRT. Now, what I want to do now is, since they have the same temperature, let's say this one will be what? E mono over 3/2 nR equal to T. Then will be equal to the temperature. If you make temperature, so the formula here also what? E, energy of the diatomic gas, 5/2 nR. So now the two of them have the same temperature like this. So this one can cancel this, then this can also cancel this. So what I want to have now, these two will go up. We have 2E of dia over 5 is equals to what? E mono 2 will go up over 3. So that this one can cancel this also. So what is E of diatomic is equal to, this 5 will go there. We have 5 E of monoatomic gas divided by 3. So what I want to have is what? 5 times 3.7 for mono times 10⁻³ divided by what? 3. So what I want to have now, I want to have 5 times what? 3.7 divided by 3 will give us what? 6.2 times 10⁻³ joules. That's option B. Don't forget that for mono, the rotational what? Motion, the degree of rotational motion is different from the degree of what? Number of degree of translational motion. Then for this is for moon. Let's say the type of atom. So for mono, it is what? This one is what? 2, while this one is 3. Then the total is equal to 5. So this one is what? Degree of what? Dynamics. The degree of freedom of dynamics. So a degree of freedom of what? Of rotational motion. This one is degree of freedom of translational motion. You understand? It's 3 in a what? Monoatomic, this and 0. Sorry, this has to be 0. Altogether is 3. So what is the formula? The formula is 3/2 nRT. For diatomic, is monoatomic. This one is what? 2 for degree of freedom of rotational motion, and this one is 3 for degree of freedom of rotational motion. Then the degree of freedom of dynamics is equal to 5. So that's why it's 5/2 nRT, where n is number of mole, r is molar gas constant, and T is temperature in Kelvin. Then we have that of polyatomic. Polyatomic gas is, we have the non-linear. For non-linear, it is what? Degree of rotation is 3. The degree of translational motion is what? 3. Altogether is 6. But when you talk about linear, for example, CO2, C2, CX2, carbon disulfide, it has what? Degree of rotation of 2, and what? Degree of translational motion to be 3. Just like diatomic gas, and they are 5. So please take note of that. I've just solved for mono I'm giving you formula for mono, dia. What about poly? Take note of polyatomic will now be what? 6/2 nRT. So that is just that. This one say calculate the specific heat capacity of air at constant volume, given that the specific heat capacity at constant pressure is 993. That means they now give us density of air to be what? At STP to be this. So what I want to do now is I want to calculate PV equal to nRT. PV equal to number of mole is mass over molar mass times R density. So what do we have now? We have the mass to be given as what? Mass is not given, but we can say pressure is equal to what? The pressure is equal to, let me make PV equal to, this one is 1 already. So they give us, I think they give us this one as 1 because they did not give us molar mass. They just give us, they did not give us mass. So mass can be taken as 1. Let me use nRT first. Let me use that one. So if I use that nRT now what do I have? What? N is 1 mole. Then R will now be equal to what? PV over RT. PV over RT. PV over RT. PV over T. Sorry. Now, what is our P first? P is at STP now, which is 1.013 times 10 raised to the power 5. What's our volume? Volume is mass over density. What is mass? 1 over 1.293. So we have gotten our volume. So R will now be equal to what? Pressure is 1.013 times 10 to the power 5 times volume is what? 1 over 1.1239 divided by what is temperature? Temperature is what? Is 273 at STP. If you solve it, what I want to have is that R will be equal to 287.3 joules per kilogram per Kelvin. That's what I want to have. Press your calculator to confirm it. Now, having done that now, our CP minus CV equal to R, Mayer's formula. Now, CP is what? Molar gas constant and molar specific capacity at constant pressure. This one is specific capacity at constant volume. So this one now, what we do now is that we have gotten this one to be what they give us as 993 joules per kilogram per Kelvin minus CV equal to, what is our R? 287.3 joules per kilogram per Kelvin. So our CV will not be, take this one here, bring this one here, CV equal to 993 minus 287.3. So our answer becomes what? 705.7 joules per kilogram per Kelvin. So our answer is what? C. This one says, which of the following is the part or postulate of kinetic theory? Which of the following is not, which of the following postulate of kinetic theory is not correct? You're looking for the one that is not correct. So what we want to do now is we check all the options. There are a large number of molecules, each mass m, in uniform direction with a variety of speed. No. The first law or the first one that have to relate with that is in kinetic theory of that, that there are large number of molecules n, each of mass n, moving in a random direction not uniform direction with variety of speed. So this uniform is random, wrong. The molecules are on the average far apart from one another and much smaller much smaller than the diameter of each molecule. So what I will say to you for that question is that the molecules are what? Are not smaller than the diameter of each what molecule, rather is greater. So they are far apart is greater than the what? The diameter of each molecule. So this one is wrong. That is what make it wrong. Now the next one says what? That the molecules are assumed to interact with one another only when they are in slow motion. No, not slow motion. Only when they are what? Collide. When they collide. So that one is what? Wrong. This is what make it wrong. Collision with one another molecules or wall of vessels are assumed to be perfectly inelastic. No, it's perfectly elastic. So this one is wrong, this one is wrong, this one is wrong, this one is wrong. That means all of them are not correct. So E will be correct. Please take note of that. Calculate the gas constant per unit mass of hydrogen if at standard temperature and pressure the density of the hydrogen is dash. Now what I want to do here is to solve a problem here. And what is the problem we are going to solve? Using the use formula of what? PV equal to nRT, knowing fully well that P equal to what? PV equal to mass over molar mass times RT. Also, what we are going to do now is P. Let us bring this mass, this molar mass. Let's bring this mass under this one. So I want that PV. Let's take mass under. If mass cause equal sign is at the numerator before it now become at the denominator equal to RT over molar mass. What again? Don't forget that we are looking for the calculate the molar gas constant per unit mass. Molar gas constant per unit what? Mass of hydrogen. So we are looking for this. This is what we are looking for. So how do we make that one the subject of formula from here? Is to divide all through by T again. So I want to have PV over mass times T, or times 1 over T. If you multiply both sides by 1 over T to remove the T, this one will cancel. So we are left with what? R over M, which is molar gas constant over mass of hydrogen. Mass of hydrogen will be represented by molar mass. Then volume over mass is density. So I want to have what? Pressure times what? 1. Volume over mass is inverse of density. So times 1 over density, because density is equal to mass over volume. So what we are seeing here is inverse, equal to mass over volume, then equal to R over M, then times 1 over T. Don't forget there is 1 over T here. This one is what? Inverse of what? Inverse of density. We don't even need this one again. Don't need this one. So now, having done that, what I want to do now is what? It will now become R over M equal to pressure over temperature times density. So what is pressure now? Pressure is 1 point at STP 1.013 times 10 power 5 divided by what? 1 density temperature is 273 times what? Density is 1.9 given to us on the board here. So 27 STP, temperature at STP is 273 Kelvin. So we now divide. If you divide it, we divide it 1.0313 times what? 10 to the power 5, 273 divided by 273 times 1.9. What I want to have is 195 what? 0.2. 95 what joules per kilogram per Kelvin. So this is what the gas constant per unit mass of what this is molar mass of hydrogen per unit mass of hydrogen. So this is the answer to that question, and that will be none of the above. An internal combustion engine has an efficiency of what? So efficiency of the combustion engine is equals to what? 28% at the fuel consumption temperature of this temperature of 927 degrees Celsius, and exhaust temperature of this. So this one should be Ti, high temperature. T low is what? 447 degrees Celsius. What is the difference between the efficiency of the ideal Carnot engine operating at this temperature and this particular engine? So the engine is what? Of this is equal to what? The efficiency of the Carnot engine is equal to what? 1 minus Tc over Th, or we can write as Th minus Tc over Th. So what do we have now? Th is what? 927 plus 273 minus 447 plus 273, convert to Kelvin, divide by what? 927 plus 273. After we have gotten it, we will now convert to what? Percentage. So if you do that, you are going to have it as what? 927 plus 273 is equal to 1200 minus 447 plus 273 is equal to 720 over 1200. So 1200 minus 720 divided by 1200 times what? 100. So we're going to have 40%. How do you get the 40%? Multiply the result times 100. This one will give us 0.4. Let me write it like this: 0.40. So in percentage, the Carnot becomes what? 0.40 times 100%, 40%. That is our answer. So we now go the difference between this and this. Then what is the difference between the efficiency? Will now give us what? Will now give us 40% minus 28%. What will give us is what? 12%. That's the answer. So that is what I'm going to have, 12% on the dot. Now this one say, what is the average transition kinetic energy of molecules in a gas at 53? Average transition kinetic energy of molecules of gas is 3/2 kBt. So what I want to do is 3/2 times kb is what? What is the value of kb? Because they did not give us. Kb is what? Is kb, I'm talking about kbt. Also giving to us, since they are not giving, is 1.38 times 10 square minus 23. Don't forget, kb can be gotten by what? Your R over Avogadro's number. That is your kb. Times what? Temperature in Kelvin is 53 plus 273. So what we want to have now what? 1.38 times 10 power minus 23 times 53 plus 273 divide times 3 divided by 2. So I would have 6.748 times 10 to the power minus 21. So if you do it, you have approximately 6.775 times 10 to the power minus 21 joules. So option what? G. So that is our answer. Don't forget this translational what? Kinetic energy is equal to 3 over 2 kBt times t. It's also the same as 1 over 2 mv square. Where this one is, v is what? The root means square speed. That is what this one is. Same as square root of what? 3 kBt over what? M. If you make this one subject of formula, this what we call the root mean what? Square speed. So that's what we call it. So I believe we have ended this section. Please follow us, liking it, and comment. Thank you.